And this isn't the best way to learn because you're kind of like constantly having your focus interrupted. But at least it does let me like, what? Yeah, at least it does let me like learn a little bit here and there. Okay. Continuing. For every inclusion of one time window into another, the behavior type B is responsible for providing a restriction map. We say a behavior type has composable sections when, for any two overlapping time windows, behaviors over the first that match behaviors over the second can be glued to form a behavior over the union time window. Let me think about that. So, for example, with the movie, let's say that we have two intervals that happen to overlap. And for each of them, there's the set of all possible excerpts from the movie that are of that length, which is basically just like a little sliding window across the movie, the first 5 seconds, or start at, the beginning plus 1 trillionth of a second, and then from there plus 5 seconds, okay? So that's one interval, I believe. Unless you have to choose, whatever. Then we choose like a small interval, like 3 seconds. And for where they are overlapping, there's a set of excerpts or clips from the film that are 5 seconds, and there's a set of clips that are 3 seconds. Let me just think about this. So far it's in this case it seems like if you had a 5-second clip, oh yeah, let's see in this case I'm not sure if we have a 5-second interval, should we permit 3-second clips to be in there, or do they have to be exactly 5 seconds, or can they be 5 seconds or less? I'm sure we'll figure this out, but in this case, I'm just gonna assume that even in a 5-second interval, we're allowed to have a 3-second clip, and so that in that case, we can imagine there's 3-second clips in the 5-second interval, and then in the 3-second window, depending on if they line up, you have like the exact same set of clips. So you could say that they agree, is how I would say it, but they call that gluing. I think that's a term from topology or something, so we'll see. So the behaviors that match can be glued to form a behavior over the union time window. Okay, so I was thinking intersection. For any two overlapping time windows, also another typo, for any two overlapping time window, behaviors over the first that match behaviors over the second. Okay, so now by match, they don't mean like are identical, but they mean, I think, have some kind of like correspondence or continuity. That's what gluing is you stick them together, but you can't just stick anything together. Like if I take like a 5-second clip from Lord of the Rings, and then I take another 3-second clip from like the end, the first ones from the beginning, you can't glue them together. But if you can determine somehow, oh, this one leads perfectly into that one, then we can glue them into like an 8-second clip or something, or maybe like a 7-second clip. Okay. Although many behavior types have composable sections, not all do. So far, it is required. Restriction maps are required. So for any, let me double check this. For every inclusion of one time window into another, the behavior type B is responsible for providing a restriction map that restricts each long behavior to the short time window. So if I understand correctly, it is what I think you could call as downward closure is actually, or sort of like a transitive set or something. It's kind of like that. But this is in terms of containment, like subset containment. So I think it's might be related to the definition of topology. I'll think about that. It seems like so far it is required to be what I'm calling downward closed. But it does not have to have composable sections, and composable sections are when you can take two overlapping time intervals and like presumably you already have the ability to form the union of the time intervals just based on how they're defined, but it's not necessarily the case that you can take the union of the behaviors occurring on some of the behaviors or all of the behaviors occurring on those time intervals. So if you can, it's called composable. And I think, I need to think about this, but I think that's their way of basically saying that it's functorial. Like if there's a functor from time to behavior, but we'll see. Okay, here we get a little bit of math. The sheaf of monotonic functions, 2R. So I don't know the definition of sheaf yet. I believe monotonic, one second. Monotonic is a property of a function which is in regards to or in relation to an order, I think. Or yeah. And then there's different kinds of orders, so I don't know if it applies to like, you know, pre-orders, partial orders, total orders. Okay, but let me think about this for a second. So let's say you have let's say your domain has some kind of order. I'm going to see if I can get away with a pre-order. And then I'm going to say, well, x is less than y. And then I have a function, f of x, and I have value f of y. Monotonic just means that f of x is also less than f of y. And I want to think about that for a second. Because orders are relations, and relations are sets of pairs if they're binary. So let's say, one second, x is less than y. So let's say I have x is less than y is less than z, x is less than z, y is less than g, blah, blah, blah. Y is less than h, c is less than z. Okay. And then I have a function. Oh yeah, this is kind of weird. See, in mathematics, you think you understand things, and then you actually try to define them, and you realize there's like so many possibilities for like how to define this, what they could mean, what the implications are. Okay, so function, if I were to take this ordered pair, so we're going to assume that the relation is defined on all the elements of a set, and the function is going to be defined on all the elements of that same set too, just for now. So presumably we're going to have f of x, f of y, blah, 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 all these different values. And in order for that relation to apply, I'm going to say that it's going to have to be what I'm calling an endo function. It has to take values in the same set, because that's what that's the set that the relation is defined on, unless we want to just have like a mapping from an order in one set to a mapping on another. Maybe that's really not that hard, but I'm going to stick to like an endo function. So algebraically, I believe we have a set of elements, and then we have a function from that set back to itself. And now I want to think about like, how does the arity of the function, like, does the arity of the function matter? Well, yeah, it could, because if it's more than binary, then we're going to have to think of some kind of more complicated rule regarding orders on each of the arguments, I think. I mean, I'm sure there's different ways you can like kind of organize an analysis of that, but it makes me think, for now, I'm just going to stick with one variable. So we have a unary function, one variable, an argument on one element, or sorry, a function on one element. Okay, so then we have f from s to s, and then we have this relation. Actually, I'm going to write something else. Function is a subset of product, so it's actually a subset of s squared. And where by squared I mean the Cartesian product of two sets. And this is already making me think about weird stuff. And a relation on S is going to be the same thing, actually. A subset of S squared. And so now I'm wondering, it's a subset. It's making me think that like sometimes expressing functions and relations as sets of pairs or sets of tuples is sometimes it's revealing because it reminds you this is the actual definition, but sometimes it might confuse you because when you just list out all the ordered pairs, you no longer see the algebraic structure. So I'm just thinking like, God, yeah, this is interesting. Another thing is that I think most algebraic structures that are like common to study for a beginner are based on binary operations. Like a group is has a binary operator, and I'm just thinking like, how do you study a unary operator? How do you study that algebraically? You know, like if for a group you can draw out the like, I think it's called the Cayley table, like all the variables. Well, I guess we can just do, you know, a column or something. But I'm just trying to think about, like, we have all these properties of binary relations, like there's an identity element, associativity, and so on. And it's like, what interesting properties are there for unary functions? Like, are there even any? I think there are. And I think that keeping it simple, I'm only going to use, wait, let me think about this. There might be an argument to be made that there is like nothing, there is nothing for you to kind of modify. Because I'm just trying to think about this as informal logic. Like if we start out without any like functions or operations defined, one second. So we would have like, if this was binary, f of x, y, what are some things that we can write to express like algebraic properties? You can say like f of x, y equals f of y, x. So there we go. That's like commutativity. Or you can have f of x e equals x. Okay, or f of x e equals e. I don't know what that is called. It's like an annihilator element. Okay, so now if we just do with one variable, we can do stuff like f of x equals x. That's like one of the few variations we can do, is like, okay, it's an identity function. Or I think we could have a distinguished element. So we could say like f of x equals e, or f of e equals x. But it just feels like it's really limited, and I'd like to confirm this later. Like syntactically, there are almost no properties of unary functions, I think. And I'd like to kind of prove why that is. Okay. Coming back to this now. Monotonic. So yeah, so my attempt to kind of think about monotonic functions more algebraically. And sometimes it's just good to recognize what your question is and then stop stop working on it, because you can come back to it later once you identify what the question is. I think the question is like, if relations are ordered pairs, see, this is already something interesting to me. Both functions and relations are sets of ordered pairs if they're binary. I'm just going to stick with that simple assumption. And yet there's a common notation for relations where you put the relation symbol in between the two elements. And for functions, there's a common notation where you put the function symbol first, then the left-hand element, and then the right-hand element. And so we might ask, why can't we write relations in the functional notation? Or why can't we write functions in the relational notation? And this is something that I already feel like I know pretty well. Okay, so there are certain additional like axioms, I think you call them, or criteria on functions compared to relations. It can be said that it's left total. I like the phrasing left total and right unique, but I've also heard someone say just well defined, and I can't remember the other term they used. Yeah. So so what that means is like, it's interesting to think that the notation itself is not that well suited for the other thing. So the function notation, like f of x equals y, or f colon set x to set x or something. It's almost like this notation invites me to write f of and any value in the set of the domain. But the problem is that if it's not a function, or if it's not well defined, or if it's not left total, it's like I can write things that are not defined. You know, like if I write f of 3 but it's not defined on 3, it's like, oh no, the notation broke down or something, because that doesn't have a value. But then for relations, it's like, okay, if I have 3R4, one second. Yeah. Maybe I'll put it like this. It's more natural to write relations as ordered pairs, because when you look at a collection of ordered pairs, you're not asking yourself the question like, oh, well, what about this ordered pair? If it's not in the relation, it's not a question you can ask. But as soon as a relation becomes left total, the fact that you know that every element in the domain is included, I want to find a deeper way to think about this, but it changes like the conceptualization, because yeah, it's like it allows you to start thinking about it in terms of dependence. Like, I know that for each of the elements in the domain, I know that there's a return, kind of. So yeah, there's more to be thought about that. I'm still just gonna think aloud about this question of like, could there be any kind of algebraic, anything interesting algebraically about like unary functions, like especially endo functions? So yeah, I think there is. I think I see this better now. So for example, like if I have a binary operation, I don't know if there's a difference between operator and operation, and I think operation is just means endo function. I keep using the word endo function, and I realize it's yeah, that's probably what an operation is. So what I'm talking about is a unary operator or unary operation. Yeah, and okay. One famous unary operation is the negation symbol in logic. And so for example, in logic, like let's say we have a set of two values. So we have 0 and 1. So we can just easily write out all the possible unary operators. So we could have 0 gets mapped to 0, 1 gets mapped to 1. Oh, sorry, 1 gets mapped to 0. And I believe that's called like the falsum or something. The falsum, but that would be the falsum unary operator. It's kind of interesting. Then you have 0 to 1, 1 to 1. Then you have 0 to 0, 1 to 1, and 0 to 1, 1 to 0. So 0 to 0, 1 to 1, it sounds like some kind of, identity operator. 0 to 1 and 1 to 0, let me think about this for a second. Like, I could define it in terms of logic or binary arithmetic, but I'm trying to not assume the existence of all these operations. I'm just trying to start out in like set theory and like logic, just basic level. So let me think about this. So we have a set of two elements, 0 and 1. Now, the first thing that we have to do is form the product. Now we have 0, 0, 0, 1, 1, 0, and 1, 1. And any subset of that set is a relation. So we can have a relation which just relates 0 to 0. A relation, yeah, so you could just choose one of them, you could choose two of them, a relation which relates 0 to 0 and 0 to 1. And I think I have to take a lift ride now, but I'm clearly like thinking about new things, so I'll come back to this. But I'd like to conceptually interpret each of those unary operators.
In 300 feet, turn left.